I've never seen this red guy. Oh, bro, I have like a picture from my belt. No, she's not throwing, bro. She's not.
She either never retires, why don't she retire since she's done?
Is she old?
I don't know, like, I was like, she's pregnant and I like. I said 80. I was not why would I understand.
Oh, I remember.
You're asking what happened. She asked. That's the movie interaction.
Yeah, like.
I said all the A's.
I say over.
So if it's 25.
You know?
I wanted to ask him a question because I wanted to ask him like if I had to write like because on the
Oh, you know what? Okay.
when you derive it, you made it so like it said like so I was gonna ask him like if we had to do that. And he goes,
Why would you ask that?
it's like I didn't know if we had to derive like that far back. He goes, sit down. Sit down.
I literally raised my hand and then he was like, do this, do this.
Just start with that.
Like, prompting me to ask a question. I started asking and then he was like, stop.
Oh my god.
Yeah, I wanted to. He was like scared of me. He was trying not to listen. I was like, bro, it's like.
But like, I lottery stuff, you can
Not
single
study
buy
for
that.
these
Y'all know what I'm doing for Easter's birthday.
All right.
Thanks. Oh yeah, 14.
Okay, so we'll
And 5, 6 labels.
start 10.1 notes, and then second half of class we can continue reviewing, maybe talking about some of the area problems, port area problems that I think some students have questions about. And then this afternoon I will have another help session doing test review, and then tomorrow morning I'll have a help session. We can treat worksheet 3 as the morning review, so I can go through any of those problems or any problems from the packet tomorrow morning or this afternoon, and then I will record those sessions and then also send out a Teams link if you want to join virtually for tomorrow morning's help session. You will get to use your calculator, and then the formula sheet on the back is good for you to know what formulas to memorize and work towards. All right, so here's, we're moving into our last unit. So we're going to talk about converging and diverging series. And so we're just going to focus on these tests for convergence leading up to the halfway point of this unit. We'll have a quiz after our break, and then the remainder of February into the beginning of March, we'll finish off the second half of Unit 10, and then we should be able to begin our AP review second week of March. Okay. All right, so. Right, so writing terms of a sequence is just a collection of numbers that are in a one-to-one correspondence with the positive integers. So we're not adding anything together. We're just finding the second term, third term, fourth term, fifth term. So for instance, the sequence of this, or the terms of the sequence will be -1, 5, -7, 17, -31. We can kind of just go through these and convince ourselves that these are the values for the sequence. So if I want to find the first term, I'll just replace n with 1, and I should get -1 here. So let's just see if this actually works out. So a sub 1 equals So -2 to the first power is -2. -2 plus 1 is -1. So that's the first term. Second term. Replace the n with 2. -2 squared is positive. 4 plus 1 is 5. -2 to the third power is -8. -8 plus 1 is -7. Okay, so on and so forth. Okay, we're always going to be given a rule, and that's how we find the sequence. Okay. So a monotonic sequence is a sequence where the terms of the sequence never decrease or never increase. They're always going. They're always just increasing, or they're always just decreasing. Okay. A bounded sequence is where there is a ceiling, where no matter how many terms we find, that nth term is always going to be less than some upper bound. Okay. A bounded sequence can also work the other way, where no matter how many terms we find, it's always going to be greater than some lower bound. Okay. Now, an infinite series is when you take a sequence of numbers and you add up infinite numbers of terms. So here I have a summation notation to indicate that I'm adding a bunch of terms together. So if I have the summation from 1 to infinity of a sub n, that just means I'm doing a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n. Sometimes the series adds up to infinity, but then sometimes the sum may add up to a number that we can predict because it's getting closer and closer towards a value that we can see. A partial sum is the sum of the first n terms. Could be the first 2 terms, could be the first 5 terms, could be the first 6 or 8 or 10 terms. So a sub n versus s sub n. A sub n is an expression that gives the nth term in a sequence. S sub n is an expression that gives the sum of the first n terms of the sequence. So S sub 1 would mean the first term. S sub 2 would mean the first and the second term added together. S sub 3 would be a sub 1 plus a sub 2 plus a sub 3. S sub 4 would be a sub 1 plus a sub 2 plus a sub 3 plus a sub 4. So it says use the following sequence to find a sub 4 and s sub 4. A sub 4 is just the fourth term, but s sub 4 would mean that I'm adding that partial sum up to that fourth term.
Is there a way to do like faster for?
Yeah, the calculator can do some of it, but right now we don't have to worry so much about having, partial sum is not going to be something that is going to be typically asked on the AP exam. It's kind of like more of a background information that we're going to need. So here's the relationship. If I were to add up all the terms, a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n, that's the same thing as the limit as n approaches infinity of s sub n. Okay. Because this has within s sub n, there's we've already added all the terms, so this would represent the sum of all the terms added together. Actually, yeah, we will do some of the calculator work today. Second page. All right, so for the infinite series, the nth partial sum is a sub 1, s sub n is a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n. If the sequence of the partial sum converges, that means it approaches a number that we can predict to some number s, then the series of the sequence of numbers from 1 to infinity also converges. Sorry, I'll do that. The limit s is called the sum of the series. So sometimes looking at the partial sum can give us information about what's happening to this, to the sum of the series. Likewise, if my partial sum is diverging, then the series diverges as well. So partial sum just kind of gives us another way of looking at the series. So let's find the partial sum for this series. Let's just list out a bunch of terms here. So if I were to add up a few terms here, or list out the terms in the sequence, it'll be 1/2, and then the summation indicates I'm adding these numbers together, plus 1/4, because if I plug 2 in for n, 2 to the second power is 4. Plus 1/8, plus 1/16. Okay, so on and so forth. Now the partial sum can give us another way to look at this series. So the partial sum, s sub 1, that's just going to be the first term. That's your a sub 1 and s sub 1 is always going to be the same. S sub 2 is just what? We do what to get s sub 2? Yeah. 1/2 plus 1/4. Okay, right now I'll do the math for us, and then I just want us to look at the pattern here. S of 4, I can just think of it as, oh, the previous partial sum plus the next term, right? I can save for the time. So the partial sum was 1/2. then it's 3/4, then it's 7/8, then it's 15/16. Can we kind of predict what this sum of the series is headed towards? Not 0, but getting closer towards 1, right? So that's the nice thing about partial sum, and that kind of gives us an idea of where the series is headed in terms of its sum.
So it converges to 1.
Yeah, converts to 1. Let me have you guys write this down here. An easy guess is that the partial sums are getting closer towards 1, and the sum converges to 1 since the sequence of the partial sum approaches 1.
This is kind of counterintuitive. Each term is getting smaller and smaller. You add them all up, so they only have 1. Yeah, that makes sense. I thought it was intuitive.
All right, number 3. Here we can use the calculator. Use the calculator to find the partial sum S sub n of the series for n equals 200 and n equals 1,000. So we can make the calculator find these partial sums for us. And if each term is decreasing small enough, then we should be able to see that it's converging towards a number. So what we're going to do is you're going to go to math, and you're going to select math option 0. You're going to see a summation show up, and we can just type it in as we see. So math 0. Should be a nice math print there for us to type in. So you can just type in x starts at 1.
It doesn't matter if it's data, right?
Oh, it should, yeah, probably doesn't matter, but if you want to take it back to rectangular form, but theta should be fine. I know you're in polar form because in the previous unit. Try it though. We should arrive at the same value. So I'm just going from 1 to 200, and then my expression 10 over x times x plus 2.
Okay.
So 200 terms gave me 7.45, and if I replace the n with 1,000, it's slightly larger, but you can definitely kind of tell that even with 1,000 terms, it's still under 7.5. So we can probably safely say that the limit as n approaches infinity for my partial sum is going to approach 7.5.
I got the same answer, Dave.
Yeah, good. So that theta or x doesn't matter. Yeah.
It's 13 and 36x. That was a lump of sticks. They crashed my calculator.
Okay, number 4. Does the series converge or diverge? For number 4. So let's just test out a couple of numbers here. Excuse me. So this is basically 1 plus 2 plus 3 plus 4. All right. My partial sum, S of 1 is 1, S of 2 is 3, S of 3 is 6, S of 4 is 10, S of 5 is 15, so on and so forth. So my partial sum, is it approaching any number? So what do you think? Does this series will converge or diverge? Diverge, right? Because okay, so I know that right now we have very limited information, but can you predict what it would take for a series to, an infinite series to converge? If we're adding up all those terms, what would need to happen?
The final term should approach 0. It should get smaller.
It should get smaller. It should at least get smaller, right? If every term is getting larger, I have no chance to converge. But the big idea is that not only does it have to decrease, it needs to decrease at a certain level. It needs to decrease fast enough so that it can converge, right? Because if we're just adding, there's a line, right? So we're going to discover where that line is. If we're adding every term is smaller, it may not be enough to converge because we're still adding infinite number of terms, so it does need to be small enough. So the big takeaway for today, we're going to discover later this week, is that it needs to at least get smaller, but we're going to discover where that line is, right? There's that line where if it's not getting small enough, fast enough, it's not going to converge. But we obviously know that if the next term is not getting smaller, there's no chance of it converging. Okay? So we're just playing with this idea for this half of this unit is, does a series converge or diverge? And we have all these various tests that we're going to go through this unit. Okay, so I just wanted to introduce this topic, and we can kind of pick up where we left off on Wednesday, but I'd like for us to look at some of the test review from our packet. Okay, so if we can switch over to that. Guys, I had a help session this morning, and the students who are here, I think the questions that came up the most are just area. I think polar area is what it just feels like the most, the most involved, and in terms of, I think that's what we need most practice with, right? So I just want to, I have up here on the board, I think these are things that we can arrive at by looking at a calculator, by creating a table of values. But I think it's also good if we just memorize these, because if we can memorize these, it kind of it just speeds up the process, and we already know by looking at what category of graphs what the cycle is going to be, and it just makes things a little bit easier. So let me just run through what those are. first is if I have a circle, like r equals 3, r equals 5, r equals 6, that is going to complete its cycle between 0 and 2 pi. There's also another circle involving trig, like 3 cosine theta or 3 sine theta. Those are, symmetrical about the x or the y-axis. These circles are not centered at 0, but that 3 is also, it tells us what the diameter is. It tells us it's symmetrical about the x-axis, but it completes a cycle from 0 to pi. So even though 1 and 2, they're both circles, they take different times to, different cycles to complete. All right. Any of the limacons, whether the coefficient is larger or smaller than the constant, whether it's a cardioid or with an inner loop or with where values don't even dimple limacon, they're all going to complete from 0 to 2 pi.
Okay, so these are only for single polar curves? Not
Right, single polar curve. Right. And then next up are the rose curves. The rose curves are the ones with the different petals. If we have an odd number of petals, like cosine of 3 pi or sine of 7 pi, or sorry, 7 theta, or a cosine of 3 theta, those will complete its cycle from 0 to pi. Right? And we know that whatever number we see there, if it's odd, that's the number of petal we can expect. Right? 3 theta would be 3 petal, 5 theta would be 5 petal. But if it's an even number, if it's an n theta, then it'll take twice as long to complete because it's creating double the number of petals that we see, or the number that we see. If it's 2 theta, it creates how many petals? 4, right? If it's 4 theta, it'll create 8 petals. So this kind of makes sense, right? That if we're creating more petals, that it's going to take a little bit longer to complete. Right? So this should make sense to us. So I think just knowing this, I mean, we can always do this. We can always, create our theta and then go through our go through different unit circle values to see where our graph is headed. But I think this speeds up the process a bit if we know these ahead of time. So I want to run through a couple of problems that students had questions about. Let me start off with page 4, number 16. I want to point out that anytime I see a problem that is asking about the area of an inner loop or the area of inside a petal, I find those to be a little bit easier because I know that, okay, if I can just get to my polar zeros, then I know that that's where my petal or my inner loop will close off, right? So anytime I see area of an inner loop, area of a petal, I'm always going to polar zeros, right? So, so those feel easier because I know that if I can get to my polar zeros, I know consecutive polar zeros will close off my region. And then once I can get those, that's the hardest part, right? With single curves, if I can find those bounds of integration, then the rest is just remembering the rule and writing it down.
It's the same for petals.
Same with petals, yeah. Petals are, area petals I think are easier because as is inner loop, because I can just get my polar zeros and I'm pretty much at the end of the problem. Okay, 17. So 17 says, find the total area of the common interior of the polar graphs of r equals 5 minus 3 sine theta and 5 minus 3 cosine theta. So I have this drawn out here where my 5 minus 3 cosine theta is to the left of my 5 minus 3 sine theta. Now I know that I need to involve intersections, right? The intersection is going to be where a transition is going to happen from one graph to the next. So polar zeros is not going to, is not, you know, we don't do that here, right? Because we don't see any region involving things getting closed off around the polar zero. So this is where I'm going to go. I'm going to go to my intersection. So I'm going to set the two equations equal to each other and then just solve it by hand here. Here I get tangent theta equals 1. So I find my intersections being 5 pi over 4 and pi over 4, first and third quadrant. All right.
Mr. Yang,
Mm-hmm.
to what extent do you want us to show our work on the test? Like if we have an integral,
Mm-hmm.
we just do it in the calculator and just say the answer.
That's right. Yeah, I do want to see where you get your intersections from. But once you're here, then, I mean, the rest is calculated. Is that what you mean? Yeah, so you don't, I'm not going to ask you to do any power rule for these or any rules. We got to, once you get here, it's just plug in the calculator, right? So I'm going to ask you for, you know, where you got your information from and then your setup, right? The majority of your points is with your setup. If I can see your setup is correct, then that's pretty much, yeah, what I'm looking for. Yeah, same as the AP exam. AP exam, they'll probably ask you for the setup, or they may ask you for the answer, but they're not going to ask you for the work in between.
And does that also apply for some of the like parametric equations where where it's like the integral of the square root of x prime squared plus y prime squared?
I will specify. If it's a problem that like you can involve sine squared plus cosine squared equals 1 and work it out by hand, then I'll specify in the problem, show me your work, like as if you didn't have a calculator. Obviously, you can use a calculator to check your answer, but yeah. But I'll specify on the test. So, so we see that in order to get this common area, we need to involve two integrals, right? Because one integral will take care of a region involving one polar curve, and then the other integral will take care of the polar region involving the other curve. So let me draw this out here. I'll draw this in red. So the red curve is the 5 minus 3 cosine theta. And the intersection is between pi over 4 and 5 pi over 4. Now, I'm going to do this one first. I'm going to take care of, now we know that I have these red segments drawn to show that anytime we do area, we have to kind of come out from the origin, right? It has to build out. We can't do this and just say, oh, this minus this, because that's not how polar works. Our polar area, we're kind of fanning out from the origin out to these radius values. So what if I can say for my inner region that involves the 5 minus 3 cosine theta, that it's going to be from here to here, right? We can see that it's from here to here. But it feels strange if we say from 5 pi over 4 to pi over 4, because that's not one continuous section, right? We can do from 5 pi over 4 to 2 pi, and then from 0 to pi over 4. If you want to do that, you can. But if you want to get it into one integral, let's go backwards, right? Let's go back, rewrite 5 pi over 4 as something that's to the left of the polar of 0. So if I subtract 2 pi, 5 pi over 4 minus 2 pi, I get negative 3 pi over 4, which is basically the same as 5 pi over 4, but it's to the left of 0. And that way I can make it one continuous integral. From negative 3 pi over 4 to pi over 4, I'm hitting the 5 minus 3 cosine graph. So the portion in red is represented by this integral notation. Does that make sense?
Can you change the answer if I just keep it as 5 pi over 4?
If you want to do 5 pi over 4, you can, but then you will have to do from 5 pi over 4 to 2 pi, and then from 0 to pi over 4. Does that make sense? Yeah, I mean, you can do that, split into two separate regions, but I can't go from negative 5, I can't go from 5 pi over 4 to pi over 4 because that's a disconnect. Right? Does that make sense? Okay. I'm sorry? Yeah, that's true. Yeah, you can go from 5 power 4 to 9 power 4. That works too. Yeah. Yeah. Yeah, that's perfectly fine. Yeah, those are all good good options. Okay. Any questions? I think this is definitely the harder one because of that break. This one hopefully feels a little bit more straightforward because we're going from power 4 to 5 power 4. This one is one continuous section. This one is hitting the 5 minus 3 sine theta. Any questions with that? Number 18, this one we don't have to involve any intersections because it's just the circle minus the Rose curve. So the circle, I mean, you can do pi r squared even without going through integral if you want to, or you can do 1/2 r squared from 0 to 2 pi. And then we know the Rose curve has a different cycle, right? Rose curve completes a cycle from 0 to pi. So 0 to pi, 1/2 r squared d theta. There's a question about number 18 on page 13. This is worksheet 3. And if you haven't gotten to it, that's fine. You can work on it at your own pace. So this is number 18 here. I'll go over this one as our last one. Page 13, number 18. So number 18 says, find the total area in the first quadrant of the common interior of r equals 4 sine of 2 theta and r equals 2. So common interior, so it's got to be a region that is inside the circle and inside the petal. So we definitely have to involve intersection because there's going to be a transition into a different graph, right? So it's going to start off hitting the petal, but then at some point it's going to transition to the circle. And we know that transition point, we can use intersection, so we can set the equations equal to each other, solve for theta. I got theta equals pi over 12. And this is the type of problem where I want to take advantage of symmetry. If I can just get the smallest portion possible, and then take that and multiply it by however many I need to multiply it by, then to me that feels like an easier problem. So in this case, I know that this petal is going to hit the halfway point within the first petal at pi over 4. We can do that by replacing r with 1 and solve for theta. We get pi over 4. We also know that this rose petal is going to complete the cycle from 0 to pi, so we know the first petal is going to be from 0 to pi over 2, halfway point to pi over 4. We can also set r equal to 4 to denote this is when the petal has a length of 4. We can solve theta, we get pi over 4. So if I can find the area of this region from 0 to pi over 12, and then from pi over 12 to pi over 4, then I can just double that, and that will get me the total area in the first quadrant. So from 0 to pi over 12, I'm hitting the Rose curve. From pi over 12 to pi over 4, I'm hitting the circle. I add that up. I know that's half the region that I need, so put a 2 in front, and then the rest is calculated. Okay, so tonight, I suggest that you go through worksheet 3 and see how well you can do that, those problems on your own. But I can also walk through more problems with you this afternoon and tomorrow morning. All right, have a good